Well, welcome to today's Ask Me Anything session. Before we start, I would like to acknowledge the traditional custodians from the land that we're broadcasting. That's the Whadjuk people of the Noongar Nation, and pay their respects to elders past and present, and extend that acknowledgement to Aboriginal and Torres Strait Islander people who may be joining us today. Today's AMA is a little bit different from our usual Ask Me Anything AMA sessions, in that we will be providing a short overview, and then we'll open it up for questions. So feel free to either write your questions in the chat or keep them for after the short, very attractive and colorful presentation that Ali and Basha have prepared for you. Over to you, Ali, who is one of our visualization specialists.
Sure. Thank you so much, Anne, for introducing me. This is Ali. I'm Pawsey visualization team member. Was working with Basha on LBPM for a couple of past 2 months to have it installed, working benchmarking on Pawsey and make it ready for the research community. Let's go through the presentation. I put some very brief introduction of the LBPM together, just a couple of slides, just to go through LBPM. Maybe some of you guys, you are not familiar with LBPM. I know that all of you are very sophisticated in CFD domain, but this is, I believe, is some sort of a bit novel and new in the community because it's focused on porous media. Yeah, porous media, visualization and LBPM. The LBPM I was talking about, we installed and deployed at Pawsey with Basha, part of our supercomputing team. Maybe you are familiar with Basha on some Pawsey project, especially Christopher. First of all, a brief overview over the highlights that will be covered today. We'll talk about the LBM, Lattice Boltzmann Method, use cases, and integration or deployment in porous media. The key differences between LBM and LBPM, Lattice Boltzmann for porous media. Talking about the features, showing some showcases, sample result example would be next, and then some other porous media tools that potentially could be offered as a service, as an official service in the future. As you may know, CFD and LBM in a specific that we are talking about today, we are focusing today, is mostly applicable and being used in mega scale, in bigger scale. Fluid flow in the chamber, simulating airflow by air condition, or so there would be so many examples of the LBM in CFD, and maybe many distribution as well. But what about the porous media? Porous media in terms of geometry is completely different to conventional CFD simulation, because user doesn't have any control over the geometry, and geometry is predefined. In the other words, geometry is not defined by the user, and the fluid flow behavior in porous media will be the result of the simulation. How does it flow inside the pores, the porous channels and canals? Maybe Basha would be the best person to talk about the key differences in geometry. If you can jump in, Basha, please. Yeah, about the key differences between LBM and LBPM in terms of the geometry, because the geometry, as I mentioned, is defined by the user in terms of the lattice cubes, but in LBPM, we have to remap our predefined geometry, which is a porous media, into the cube of like D3Q19, for example. Go ahead, please, Basha.
Yeah, thank you, Ali. So the key difference is, like in any other CFD simulation, we need to give the domain, and you have to, you have to extract the domain, computational domain, and mesh the computational domain. So one of the restrictions in LBM is that it has to be like a symmetric cube or a symmetric lattice mesh. So that is one of the requirement to have a stable simulation of fluid flow and heat transfer simulation. So in the CFD and conventional CFD, what do you do that you take a computational geometry and you have a liberty to mesh according to your requirement. Whereas in LBPM or LBM, it is like a regular structure of cube or squares. If you're solving 2D channel or 2D porous media, so there it has different structures. Like for example, if you're solving 2D porous media, you need to distribute the computational domain using D2Q9 lattice. So if you're simulating three-dimensional computational domain, then you have to lay the computational domain with the D3Q19 lattice. So when it comes to porous media, so as you know that porous media is like, if you take example a simple porous media, you can extract the domain easily or with some difficulty, and then you can try to mesh with the unstructured mesh, solving finite volume or finite difference. But in LBPM, it's not that simple. That you need to either you have to get the sample scan for your representative porous media, and then you try to fit the computational domain using required lattices. So it will be a structured lattice because it is a cube or a square for a 2D case. So it's a bit different from the conventional method. But in all, Lattice Boltzmann method has a very good, it can cover wide spectrum of boundary conditions when compared to conventional CFD. So the Ali is showing the simple velocity distribution of probability distribution function or different particles, which has like 9 distributions here. So it becomes more complicated for 3D case. I think Ali you can go to the next slide.
Yep, sure. Thanks for brief explanation, Basha. Just to confirm, solving and like lattice cubes, everything's identical to LBM in LBPM. The key difference is remapping the geometry from microcity predefined geometry, which is our predefined geometry, into the cube lattice. For more information, I put the GitHub page here that you can grab some information from to get more familiar with if you're not. And to mention that this is a part of the bigger project, Open Porous Media project on the right. And there are some potential upscaling as well. I haven't gone through the integration of the LBPM into that sort of upscaling techniques to just distribute or extract the porosity or actual relative permeability or absolute permeability from a small core sample into the basin, for example. But totally depends to the interest level of the community. To be honest, today's session goal is gauging the community, research community interest in this project, because that has a very, very high potential of deploying bigger and bigger projects integrated to each other. So everything depends that we go into this direction or not. We did benchmarking as well. This is a very sophisticated tool, has been developed on CPU as well as the GPU. You can see that a single GPU on single node perform 18 times better than 216 CPU across 8 nodes, 27 tasks per node. The result was, the sample was 200 cubic. And I do remember, I did it like 2-3 months ago with Basha, and that was, I believe CPU time was like 5 minutes or 10 minutes, something like that. But GPU was done in 12 seconds or something like that. That was quick, very quick. You can assume what does happen if you have it distributed on GPU mode using more than one GPU across distributed nodes. So the workflow is fairly simple. Preparation, which is image segmentation and decomposition. Again, if you have worked with the microcity data, the scanner outcome, X-ray scanner outcome is like grayscale, and you need to segment it into separate phases to distinguish, for example, solid with other, like, I don't know, could be many things like sediments, like other things. If you have coal, for example, you will have, I don't know, some sort of other solids, and pores, which is very important, how to distinguish the border between the porous space and the grains. That is a very like a very deep discussion, image segmentation itself, how to reach to the most real kind of representation of the real data. Everything could go easily wrong if that segmentation is not representing the real data. Then you decompose it to the number of the CPUs or GPUs that you have. For single phase, CPU only module is available to calculate the absolute permeability from relative permeability. It is available in GPU as well as CPU. Color simulation is similar to LBM. You need to add some extra parameters, if I remember correctly. And before that, you need to apply some morphological modification into the sample to make it ready for multi-phase simulation. And features.
Ali, I just want to comment on this.
Yes, yes. Please.
So here the color simulation is like this technique used for one of the techniques in simulating the multi-phase flow for immiscible fluids. So if for single phase, you don't, the simulation is just using simple parameters like single relaxation factor and so on. So for color simulation, you need to specify relaxation factor for various fluids in the simulation.
Yep, perfect. The features that makes LBPM bold compared to others. I was working with different tools in Porous Media for long time, but the thing that really makes this LBPM unique is the visualization outcome as well as the computation outcomes. So you will have soil output simply and like it's very quick without any time hassle to visualize it using Visit. So you do have LBPM module available on Zeus and Topaz. You do your simulation on CPU or GPU, whatever. You have everything saved in your Scratch, and then you come to web-based remote with services. You launch Visit. Already file system is mounted there. You just go to the directory and load the data. That's as simple as this. Very quick. Examples. This is one of the examples that we tested the LBPM installation on Zeus and Topaz with. It is an open source project available on Digital Right portal and also in the GitHub wiki page that shows the single phase injection in Ben timer sandstone. DNA simulation and just pushing the non-wetting phase, wetting phase with non-wetting phase as invasive phase. Here is another CFT simulation results in Porous Media that I borrowed from Penn State University. It's not done with LBPM, but it's showing what you can do. One of the showcases that what you can do with Lattice Boltzmann simulation in Porous Media, doing your simulation and comparing based on grain density or grain size. Similar thing you can do with LBPM in a sphere pack at the bottom, which is again available open source on Digital Right portal that you can run drainage or imbibition, whatever, in the sphere pack, which is a ground truth, by the way, that you can check how accurate is LBPM. Sample results, absolute permeability at the left and relative permeability on the right. So when it converged on the left, it shows it stopped simulation, and that would be the final absolute permeability for single phase, and gives you the relative permeability as well, which no need to explain more. And the last slide talking about the future tools at Pawsey. As we mentioned, this session's goal is mainly for gauging the interest level of the community on LBPM and on oncoming tools, mainly around Porous Media. So Pore network modeling, this is another one that I was working on that for a long time again. The actual project is from Imperial College. Don't remember the name of the researchers. Blunt, I think that was Blunt team. And the visualization invented by myself, and I'm integrating the visualization module into the package. It is a hybrid tool, could be deployed on the supercomputer as well as Windows cluster. If you know Pawsey, you should maybe know Pawsey has a Windows cluster as well, offered for the visualization users called Nebula. If you need, you can get easily access to that. It is a pre-test system, by the way, that will be in service soon. PoreFoam is open foam-based tool, which is again distributed specifically for Porous Media. I was working on this as well with Alexis, which is not here today, from Pawsey Supercomputing team, could be another potential tool in the future. And LBM, which is Basha's project, is 2PM. It's 2D, sorry. If you have any extra information or explanation, Basha, please.
Right now we have, I'm working on 2D LBM Porous Media tool. This tool is a bit different from the conventional one, where in conventional one, they use the Boolean masking to demark the fluid and solid phases. So this tool is extracting it is using the Boolean masking to extract the computational mesh rather than using the whole computational mesh and wasting the computational resources. So I think I have got a good result compared to the other conventional method. So hopefully I'll make it public soon.
And that's the end of today's presentation. The rest of the time,